let's continue. Yeah, so you woke up again, if the coffee didn't do it. So let's continue with the first part of my 3 lectures. I didn't quite finish the first part in the first lecture. And now I'll tell you how we can infer from this Wilson loop or position operator eigenvalues a bulk boundary correspondence of topological states. So bulk boundary correspondence. And this, in the way I present it, I guess is contained in the work of Witkowski and others in 11010320 on the archive if you're interested in the details. Okay, so remember that we had defined this projection operator P of K on the occupied bands in some, in some insulator of interest, and that K was d minus 1-dimensional momentum because we were looking at a space where the x coordinate is kind of, we are looking at position operators in the x direction. And now we want to look at the boundary of a system, and the boundary is arranged in such a way that the system fills a half space that is for x larger than 0, and we have vacuum for x less than 0. So that then makes also sense that this K contains only the momenta perpendicular to the x direction, so Ky, Kz, and so forth. And now we, for simplicity, we'll look at the Hamiltonian that is spectrally flattened, as one says. So we, in the bulk of the system, we want to look at a Hamiltonian that's written as 1 minus 2 times this projector on the occupied bands. Okay, and that also depends on these momenta. So this is the Hamiltonian that describes the system in the bulk over here. So why, again, for topological reasons or for topological features, we can basically ignore the detailed energetics of the occupied bands. And what this Hamiltonian basically does is it puts the energies of all occupied states at -1, and all unoccupied states are at energy +1, right? So that's the simplified version of the Hamiltonian of the system that we are interested in. And now, to describe this situation of the boundary, we want to look at the Hamiltonian that I call H boundary. That also depends on these momenta perpendicular to the direction which we cut, and this is given by P of K times V naught of X and P of K minus +1 minus P of K. And I will choose this V naught of X to be +1 for X less than 0 and -1 for x larger than 0. So what have I written here? Why is this representing the system with a boundary? So very much on the right-hand side, we have 1 minus 2 times P of K. There's a projector, so P squared is equal to P. So we have this H flat, right? Very much on the right-hand side. And on the left-hand side, where this is +1, this P cancels out, and the Hamiltonian is just the identity. Yeah? And that means that all the states are residing at energy +1, and if we basically put our chemical potential at 0 energy, then that basically means that the states are all unoccupied on this side, so it's the vacuum. Okay, so that is a representation of the system with a boundary. And now the point is basically that we can ask what is the spectrum of this system going to be like? So the energy spectrum, say if this is a 1-dimensional system, it's easier. So what is it going to look like? So there is +1 eigenvalue, -1 eigenvalue. So the system is gapped everywhere except possibly near the boundary, right? And there's a length scale, like some correlation lengths associated with this gap. So when we are far away from the boundary, deep on the right-hand side, we have this Hamiltonian. So it means that we have a lot of eigenvalues at -1 and a lot of eigenvalues at +1, thermodynamically many, right? On the other side, all the eigenvalues are +1, right? So there's even more at +1. So what we can say is that the Hamiltonian this Hamiltonian here has spectral accumulation points at +1 and -1. And then there is this finite region, right? It's given by basically this correlation length of the system or the gap, where eigenvalues in the middle can appear as well, right? There could be some isolated eigenvalues, spectrally isolated eigenvalues in here. But the important point is that there can be only finitely many because this region is only finite for a given, you can extend this over K, right? And then there's like bands, but the point is there's only going to be finitely many bands in the middle here between the +1 and the -1 eigenvalue. And so the point is now that we can deform this boundary Hamiltonian into essentially our position operator, and we can deform smoothly. So deform into PXP. This is an operator. Maybe I should make this more clear, that this X is an operator. PXP. Okay? And one way to do that, for example, is, just very explicitly, if I choose this potential to be something like this, and I let this T, so I parameterize this now by T, and I let this T run between 0 and 1. And so basically what you see is that, so here it's a step function, right? So it's a step function, this potential. And down here at T equal to 1, it's exactly X, yeah? At T equal to 1, this is for the whole range, it's just X or minus X, okay? So it's just a linear slope. Or maybe I should like this, and in between it, basically, you're basically interpolating by having some linear part, and then it's cut off after this certain range. So you're basically you're making an interpolation between the step function and the linear slope, right? And the point is that also the spectrum should sort of smoothly interpolate between this spectrum of the initial Hamiltonian and the spectrum of this PXP. And the spectrum of PXP, we know, for example, in the case of a Churn insulator, it was, if I draw it again, I had it sort of 90-degree rotated before, but this PXP spectrum as a function of Ky, right? It was this thing that does these windings as Ky goes from -pi to pi, right? That's what we stopped with last time. And this spectrum is topologically equivalent now because of this transformation that we can do between the two systems, is topologically equivalent to this one. So you can think of the transformation as basically this goes on to infinity, right, in the case of the PXP, but you're kind of collecting all these bands from infinity and you're pushing them to lie between -1 and 1. And then, of course, there could be a subset of bands but the connectivity you have to retain, though. So you have a lot of bands at -1, but then you have the ones that flow, and then you have a lot of bands at +1, right? So that's for the Churn insulator, for example, going to be the edge spectrum. But the fact, because of the periodicity of the momentum space in this direction, you always have to connect this band back to here, so you have this one flowing mode, which is the boundary mode of the Hall, the edge mode of the Hall bar, essentially. That one you have to retain. You cannot get rid of it. And this is even true if you have symmetry. So if there are, for example, if you have time reversal symmetry and you have states which are degenerate here because of Kramers and so on, this also has to hold as long as your interpolation or your edge potential doesn't break these symmetries explicitly. So what we see is that there is a one-to-one correspondence between the spectrum of the position operator, PXP, and the edge spectrum of the topological system. It's just like one is sort of squished, a squished version of the other. So that's the key point. Okay, and now I would like to give you just, we had already talked about the Churn insulator. Here is pictorial. Let me be more explicit and sort of in terms of an explicit model for a Churn insulator, write down how that works. So the example for a Churn insulator, I'll construct it as follows. I'll construct it from something that's very familiar to you now. Well, very, I don't know, but familiar. Churn insulator, I'll define it via a two-dimensional Hamiltonian for a two-dimensional system in momentum space directly. And that system will start off with something that is like the Suschrieffer-Heger model that we've discussed before. And you remember there was 0 in the Suschrieffer-Heger model, 0 on the diagonal, and then there was a term on the off-diagonal, which was this t plus t prime times e to the I kx. And then there was t plus t prime times e to the minus I kx. That was the Suschrieffer-Heger model. Now, first of all, for convenience, I'll just set this t prime equal to 1. So it'll go away. And then you remember that there were two phases, right? The Suschrieffer-Heger phase, if this t was less than 1, and then there was the trivial phase if the t was larger than 1. And now I would like to use my other momentum, the ky, to interpolate between these two cases. And the simplest way to do that is if I write here 1 minus cosine ky. Why do I do that? Because at ky equal to 0, this part is 0, which corresponded to the t before. So we have a perfect Suschrieffer-Heger model. And at ky equal to pi, this is 2, which is larger than 1. So we have a trivial phase of a Suschrieffer-Heger chain. Now that's cool, but that's not yet a gapped phase because we know that when this term is equal to 1, the system becomes gapless. And to avoid this, I'll add another term, which is sine ky minus sine ky on this diagonal, which doesn't affect the two limits I discussed right now because the sine ky is 0 at 0 and pi, but it just makes sure that the system remains gapped at the whole interpolation of the two, right? So basically at ky equal to 0, I have the SSH topological case, and at ky equal to pi, I have the trivial case. Okay? And then I know immediately how to draw the spectrum of this thing as a function of ky. The energy spectrum. So at ky equal to 0, again, we have the energy 1 and minus 1 as a bulk band of the Suschrieffer-Heger chain, right? So these are the two eigenvalues of this thing in the bulk. And then we know we have this one end state at each side, yeah, at 0 energy. And then at ky equal to pi or minus pi, we have these bands in the bulk, and we have no end state. Okay? And now the question is, how can we connect these two? I mean, there would be, in principle, there would be various possibilities, right? It could be that this thing hangs down here, and it's rather trivial. But of course, the case that we would anticipate is the one where this state, as I change ky, actually runs across the energy gap. And that the second case is realized, you can simply see by using our chiral symmetry. But now, so remember, sigma 3 was the chiral symmetry. And now we have h of ky, and it turns out that this chiral symmetry not only maps h to minus h, but also in this case it maps h of ky to h of minus ky. You can just quickly check that. And then, since it's local in kx, it needs to be obeyed also by this boundary mode. So then, you know, if I have a state here, I have to have a state at the opposite energy, opposite k. So the only way to connect my boundary mode is this way, and it's indeed the Churn insulator that I produced, right? So it connects the two bands. Okay, and they're going to fill up here somehow. Okay. Of course, this symmetry here was only now a convenient tool to construct the connection of the state. It's not actually important for the Churn insulator at all. So once I realized that I have this spectral flow, there's no symmetry needed to stabilize this edge state. It's just there, right? And just to compute also, or to complete the picture of the Wilson loop, we know that, again, at ky equal to 0, we have this half quantization due to the SSH, right? So I put the 1/2s here, and this is where the eigenstates sit at the yellow bars, and the white bars are just the unit cells. And on the end, at ky equal to pi or minus pi, I can simply, I know that the Wannier charge centers sit exactly at the lattice side, so they sit here at my white bars. And then, you know, there's just, the question is again how to connect these two, and it turns out that they need to be connected like this, right? And it's rather explicitly now, knowing this Suschrieffer-Heger thing, you're knowing that this is a Suschrieffer-Heger chain and this is a trivial one, we already, oops, this is a little bit distorted here. We already know that we'll have this spectral flow in this way. And of course, again, whether these are exactly at 1/2 or not is not important for the Churn insulator. It's just important for our sort of deduction of the spectral flow. Right now, if I use generic perturbations which break the chiral symmetry and the inversion symmetry, they can move up and down. But this connectivity, as long as I make sure that this is a Brillouin zone, so it's periodic, and the left and the right half have to have the same spectrum, then there's no way to change this connectivity of the Wilson loop bands or the position operator eigenvalues. And that's why this is a completely robust phase, this Churn insulator, due to the spectral flow. Okay, so that was meant to be the end of the previous lecture. And now we come to the second part, which is on topological crystalline insulators. So in the Suschrieffer-Heger model, we've seen that we had this chiral symmetry which protected some topological features of the system. But this was a local symmetry. It was realized in each unit cell. It just exchanged, it gave a -1 to the sublattice, the wave function on sublattice B as compared to sublattice A. So there's a local symmetry protecting the topological properties of the system. In topological crystalline insulators, you use a non-local crystalline symmetry to protect topological features. So that's the definition. So these non-local symmetries, could be mirror, could be inversion, could be a rotation, things like that. And there are basically two ways of looking at it. One is, does this non-local symmetry protect the bulk from being adiabatically connected to a trivial bulk, some atomic limit? So that's one way of viewing this. And the second consequence that we might look for is, does this non-local symmetry protect topological boundary modes?
What's non-local symmetry?
Like something that is not implemented on that maps, a mirror symmetry, right? It maps like one part of space to another part. You cannot write it as a product over local operators, local unitary operators. You do something non-local. You're permuting lattice sites from way, one side of the system to another one.
Why is that called non-local?
But because it maps non-local, it's not a product over local unitary operators. Does that make sense in nomenclature? Yeah. I mean, you are mapping degrees of freedom of one part of the system to way over and compare them to degrees of freedom on another part. So permuting parts of the system, like a mirror symmetry, right? Like it's the mirror symmetry of this blackboard, right? Maps this half to this half, right? So it's like way other end of the system. While time reversal symmetry, for example, would be something that is just locally acting everywhere. Okay. So, and the other thing is, the other question is, can we have topologically protected boundary modes? So an example, so that these are not the same, we have already seen in the Sushri-Verheger case, where inversion symmetry, we said, distinguishes the polarization 1/2 case to the polarization from the polarization 0 case, and there's no way to interpolate between the two, obviously, because 1/2 and 0 are different, and we cannot change 1/2 into 0 without breaking the inversion symmetry. But inversion symmetry alone doesn't guarantee the boundary modes. And so here we are mostly interested in the case where a non-local symmetry also guarantees boundary modes. And for that to be the case, the boundary needs to allow for a non-local symmetry, needs to be invariant under the non-local symmetry, right? So the boundary So can in a one-dimensional system, can the boundary be invariant under a non-local symmetry? Okay. Yeah.
So I usually learned that it's an entity is just a basis of the topological chapter edge mode. So you're saying that it's actually not the same.
It's not the same. So SPT, for example, if you think again about one-dimensional systems, there are inversion symmetry protects. So you've probably heard about the Haldane phase. Inversion symmetry you can think of as protecting this Haldane phase, but if you just take inversion symmetry, the boundary mode is not guaranteed. You still have in the entanglement spectrum, because that entanglement cut is kind of inversion symmetric, you have it, but the boundary breaks inversion symmetry, so the edge mode is not guaranteed by just inversion symmetry. So can a one-dimensional system have a topological edge mode protected by a non-local symmetry? The answer is no, because the edge of a one-dimensional system is just zero-dimensional, so there's no non-local symmetry that can act on a zero-dimensional object, right? There's only local symmetries in zero dimension because there's no notion of locality anyways. So, so the second example, so this point 2 that we are interested in can only appear in 2 dimensions or higher, right? Where there is some notion of locality also on the boundary. And so let's go for the simplest possible example, and that is, so the simplest example is in 2D. So we are again interested in a system that is terminated in the x direction. So what is essentially the only symmetry, non-local symmetry, that leaves the y direction invariant. But if I don't think about anti-unitary symmetries, so the only spatial symmetry here is mirror, right? So I'm probably interested in the case where edge modes could be stabilized by this mirror symmetry my, which acts like inversion basically along this one-dimensional system. And it turns out that the simplest example is in class A3. If this table, I'm just saying that because you'll learn, this vocabulary has been used before. That is, if you don't remember what this means, is there is only chiral symmetry. Okay. C. So if you have so the Suschrieffer-Heger model was a system in class A3. It was a system that had only chiral symmetry. It was non-trivial in 1D. It turns out if you look into this table in 2D, you'll find that that class A3 is trivial. Okay. And so the point now is that when we also use mirror symmetry, then we can make class A3 non-trivial. So class A3 plus a mirror symmetry, my, can give us a non-trivial topological crystalline phase. And what we need to ask is that the mirror symmetry my commutes with this chiral symmetry C in this case, actually. Okay. To show you explicitly that that is true, I'll just write down a Hamiltonian and we can check things. So, and it's going to be sort of the same kind of spirit as before. We're just going to look at a two-dimensional system, and we'll use the knowledge of the Suschrieffer-Heger chain that we have already acquired. So first of all, I want to define my symmetries. It's good to start with that. And the chiral symmetry, I want it to be this thing, diagonal. I'll look at the system with 4 local degrees of freedom, so it's going to be a 4x4 Bloch matrix, and the chiral symmetry is going to be realized by that. And the mirror symmetry, my, besides sending ky to minus ky, it's going to act on these local degrees of freedom like that. So there's, if you want to think of some orbitals or something, there's 2 orbitals which are even under mirror reflection in y direction. There's 2 orbitals which are odd under mirror reflection, like a p orbital, for example, py orbital. Okay, so now, for example, for this chiral symmetry to be a symmetry of the Hamiltonian, the first thing I notice is that all these entries here have to be 0. So these chiral symmetric Hamiltonians in the basis where the chiral symmetry looks like that, they always have this block of diagonal form. There's some matrix here, Q, and here is Q dagger. That's the typical form. Now we'll fill in some Q and Q dagger. And what we're going to do is we're going to use this SSH chain, similar to how we constructed it in the Churn insulator. We're going to write 1 minus cosine kx plus e to the I ky. Sorry, I'll do ky here, kx here. And now, okay, let me just copy it here. 1 minus cosine ky e to the I kx. So that will be one of these systems that changes from being an SSH chain at ky equal to 0 to being a trivial chain at a trivial system at ky equal to pi. And I'll add another copy of such a system, but this time I'll add it with the opposite winding number, which means that I'll write 1 minus cosine ky plus e to the minus I kx. Okay, and then down here it's going to be 1 minus cosine ky plus e to the plus I kx. And if you remember how we computed the winding number, you remember that this was basically the prefactor of this kx, depends on whether it's like plus 1/2 or minus 1/2, the polarization. Okay, and now the only thing that I have to make sure is that that these things are actually gapped all the way and also mirror symmetric, then I can add some signs again, like in this Churn insulator example, to make sure that they are gapped everywhere else. Okay, and then now we'll look at what I have actually constructed here. So what I've constructed is, again, if we focus on ky equal to 0, at ky equal to 0, what I've constructed is a pair of Suschrieffer-Heger chains. Both are topological, and if I compute the winding number of each of them, then so the winding number is basically, it's basically this polarization, but it has integer values. Then I'll figure out that they have the opposite winding number, so there is no net polarization in this system. So more precisely, so if you look at ky equal to 0, you'll see that in the mirror plus subspace, which is wave functions of this form, yeah, and then there's a mirror minus subspace, which are wave functions of this form. In the mirror plus subspace, I am only acting on this first pair of Suschrieffer-Heger models, and I can compute. So let me let's call these things plus, right? And this is the plus wave function and the minus wave function. I can compute the binding numbers, nu plus minus I dkx over 2 pi. And then this is, I can use plus or minus, and that's at ky equal to 0, partial kx, and then plus minus at ky equal to 0. So the result that I'll get is that they are plus or minus 1/2. Okay? So the two mirror subspaces have opposite winding or opposite polarization, and now so the net winding number is 0. But now I can of course define a mirror graded winding number because I do have this unitary symmetry. So at ky equal to 0, in the Brillouin zone, this mirror symmetry is a local symmetry. It maps ky to minus ky, but at ky equal to 0, ky equal to pi, it's a good quantum number to distinguish the wave functions. And so now I can write basically a mirror graded winding number. Which I call nu, and that is nu plus minus nu minus over 2, and that is equal to 1/2 here, right? Because it's 1/2 minus minus 1/2, and this is a topologically non-trivial case, and then of course if I do this at ky equal to pi, I'll get 0 because all my SSH chains are 0, okay? And now I can basically already argue what the spectrum will look like and why this is all protected, or why there is a topologically protected boundary mode appearing. So if I look at the spectrum of this system with the open boundary conditions as a function of ky, then at ky equal to 0, I'll have these two boundary states from the two. This is then two decoupled SSH models, essentially. But they'll have opposite mirror eigenvalue, right? One has mirror eigenvalue +1, the other has mirror eigenvalue -1. And otherwise, it's just an SSH model, so there will be bulk bands here and there. And then at ky equal to pi or minus pi, I have a trivial system, so there is no, there's just bulk bands, but there's no boundary states. Okay? And then you can ask yourself, how do these things connect? And it turns out that, well, by chiral symmetry, again, chiral symmetry is now a spectral symmetry that is everywhere in the spectrum. So if I have a state here, I have to have one at minus the energy. They have to sort of close up like this, right? And so there's really a crossing here. So I have two bands, and they have to cross at zero energy here because of the chiral symmetry. And the hybridization between these two states at this momentum is protected, or cannot happen because of the mirror symmetry, right? Because these two states, the two end states, they carry the opposite mirror eigenvalue. That's just because these SSH chains live in two different mirror subspaces. So in that sense, I have constructed now a two-dimensional topological crystalline phase. And you see a little bit what the spirit is. The way I've done it is I've looked at a specific momentum at which this non-local symmetry becomes local in K-space. And I can use invariant, which is actually defined in one dimension lower, right? This is a 2D system, but we are basically looking at a invariant that is defined for 1D systems usually. But now we can look at it in a mirror-graded way. So we can look in each mirror subspace individually, and then the difference between the two topological numbers gives us the new index for the 2D system. And now there's no way, once I've figured out that this is the boundary spectrum, there's no way to remove this pair of modes without breaking the mirror symmetry or the chiral symmetry. Okay? Yes? Okay, so let's see what. So it should be sigma x. Let's try this one. I don't know. I have not thought about that. I mean, why are you worried about inverse symmetry?
Well, I mean, you have now essentially two symmetries in the game, right?
Yeah.
Symmetry, which in the first quantized representation is not really a symmetry. Funny thing with anticommuting.
Oh, here it's also funny. It's also anti-commuting.
I know.
Yeah.
They have segments on them. So I'm
Yes. Mm-hmm.
on the fundamental level, I mean, if you write that guy down in the second quantized representation, we have two actual symmetries. I mean, in the second quantized representation, chiral symmetry looks like a normal symmetry.
Yeah.
And then it must be possible to actually block diagonalize this guy in some way. So as to diagonalize both symmetries simultaneously.
But they are both diagonal. The chiral symmetry.
I would like to see a Hamiltonian which is manifestly
The Hamiltonian should be block diagonal, or the symmetries. No, yeah, this is okay, but yeah. Yeah, so I mean, for one, of course, you see that these are two, it's like two Churn insulators on top of one another, right? I mean, the mirror symmetry is basically, but the mirror symmetry changes the Churn number, right? So you're basically exchanging, it's like two Churn insulators, and you're basically mapping one to the other by mirror symmetry, and yeah, right. Yes, that's the gist. But of course, you also have to enforce the spectral symmetry for this. Yeah, right. Yeah, but yes, is that enough? I don't think I'll get very far if I write down the second quantized thing now. Yeah. Okay. Cool. Okay. So that was in 2D. Let's do something that's a little more intuitive, maybe in terms of, I mean, this is really the simplest system in 2D that has this property, but it has this chiral symmetry, so it's a little, it's a little unphysical. So in 3 dimensions, we have actually much better realizations or much better examples for these topological crystalline insulators. And the reason is that in one dimension lower, in 2D, we have a very natural and robust topological invariant, and that's the Churn number. So in 3D example, we'll use the mirror Churn number. Okay. So what we're going to look at is, again, a 3D system. Let me write down a Brillouin zone for such a thing. So that should be Kx. Here's Ky, and here's Kz. And now I want to look at the mirror symmetry. Again, I'm looking at a mirror symmetry My. So I will look at the X surface eventually. And that's going to be the same all the time in these lectures. It's always going to be the X surface. And then the key thing is to realize that there are, again, D minus one dimensional manifolds in this Brillouin zone which are invariant under the mirror symmetry. These are these planes, right? So the first and the last plane are the same, right? So at Ky equal to 0, pi, and 2 pi the same being as 0. So there are two planes essentially which are invariant under the My symmetry. And now on these planes, I can divide the occupied subspace by the two eigenvalues of My. So divide occupied bands. In the eigenspaces of plus or minus eigenvalue of My, or plus or minus I, depending on whether you have a spinful system. And then I can, so then I have a two-dimensional manifold of states, right? I mean, states living on a 2D manifold, Kx, Kz. And I can ask what is the Churn number in each of the two subspaces, okay? So this, I'll call them C plus and C minus, yeah? You get two Churn numbers, so two completely detached subspaces. You can compute this Churn number in the way I wrote before, or Ivo wrote, with just that the Barry connection is now basically just taken between states of one mirror eigenvalue. And then I can define, for example, so then I have to decide, these are two numbers which are independently topological invariants, if you wish, but now I want to look at the system with time reversal symmetry. I don't have to do that, but many crystals are time reversal symmetric, so maybe it's a good example to look at. And time reversal symmetry will say that the Churn number, let's look at a spinful system. So we have the eigenvalues of My are plus and minus I. Then time reversal symmetry will say that the Churn number of the plus I manifold is equal to minus the Churn number of the minus I manifold, right? So that's the constraint of time reversal symmetry. If that was not the case, right, then I would have a whole conductivity, because the difference between the sum of the two is the whole conductivity, is the total Churn number, right? But now I can also look at the difference of the two. That's the mirror Churn number. And so it's defined as C plus minus C minus over 2, say. And this is so the topological invariant that we are after. So it's a mirror Churn number. Okay. And now we can ask ourselves, what is the bulk boundary correspondence that this Churn number enforces. And for that, we can look at the boundary Brillouin zone of this system. So, okay, ideally I would draw it from this side, but now let's draw it from this side. So the boundary Brillouin zone has two good momenta. It's Kz and Ky. And then I have these two lines which are mirror invariant, right? And I can say something about the electronic structure on these two lines from the fact that these, that I know the mirror Churn number. So if I look at the electronic structure on this line, so it's as a function of Kz for, say, Ky equal to 0, well, I'll have some bulk bands. And then let's look at the case where the mirror Churn number is 1. What does that mean? It means that I have one chiral mode. So this means that C plus is 1 and C minus is minus 1. So I'll have one chiral mode with plus I mirror eigenvalue, and I'll have another chiral mode with minus I mirror eigenvalue, right? Coming from the other subspace because it has the opposite Churn number. So this is the case for Cm equal to 1. Okay? And now, can these two hybridize? They cannot, because these are two different mirror eigenvalues, and if I want to preserve mirror symmetry, there's no way to open a gap between these two states, right? Here it's a bit special because also there is time reversal symmetry, so they have to cross as Kramer's partners at a time reversal invariant momentum, and then, this automatically already by time reversal forbids hybridization. But if I look, for example, at the Cm equal to 2 case, then it's a little less trivial. So in the Cm equal to 2 case, there's of course no need for these two to cross at the time reversal invariant momentum, and I can just have two minus I states that go like this. And then by time reversal symmetry, the only thing I need to make sure is that the plus I eigenspace is doing, exactly this sort of Kz reversed. Okay, so that would be the case for mirror Churn number 2. Now, if I have time reversal symmetry, mirror Churn number is 1, what do I have? So the question is, how do you think about how you would close this electronic structure up in 2 dimensions? So we just made this one cut, right? And we see that these states, that they basically meet at the point. But away from this point, there's no need for any degeneracy between bands. There's no symmetry-enforced need for degeneracy. So generically, the bands will be non-degenerate in these other directions. And what you then see is that what they actually do is they form a Dirac cone in 2D. So these bands will sort of also be sort of split in momentum space in the Ky direction. And then this is a Dirac cone, okay? Now, if you have only one Dirac cone in a time reversal symmetric system on the surface, then what you do have actually is a 3D topological insulator, right? Now, here again, the 3D topological insulator doesn't need any mirror symmetry for its Dirac cone to be protected. It's only then in this case where you have this Churn number 2 that you actually need the mirror symmetry. And also here, you basically have 2 Dirac cones sitting at these 2 different momenta. So if I draw this case here in this Brillouin zone sketch, I would have 2 Dirac cones, one here, say, and they are protected. This is the entire electronic structure of the surface, and they are protected by the mirror symmetry.
You have a new Churn number of 1 without time reversal symmetry?
Yes, I mean, without time reversal symmetry, I could even have a different number of modes in one direction versus the other, in which case I'd, yeah, but yeah, you can also have mirror churn number 1 without time reversal symmetry. Then it's just such that this Dirac cone is not pinned to the time reversal invariant momentum. It could move anywhere on this line, right? Time reversal symmetry just pins it to the gamma point. No, it would then it's just mirror. Then you do need the mirror symmetry. So then it's a topological crystalline insulator. Yeah, right. How am I doing with time? Not so bad. Yeah. So so this was the case. So I wanted to look. This is the electronic structure along this line. Okay. So this is the surface Brillouin zone. This is the surface. Maybe that's where you got lost. This is the surface Brillouin zone for this system. The yellow lines are the mirror invariant lines in the surface Brillouin zone. And what I know, if the mirror churn number is say 1, then I know that along this line, the electronic structure of the system with the surface must look like this. I have bulk bands, and I have one chiral mode and one anti-chiral mode with opposite mirror eigenvalue, plus and minus I. And so that's basically the gist here. And then I have to think about how I complete this electronic structure in 2D, and then I see I get a little Dirac cone out of this. I get the Dirac cone. All right. Mm-hmm. Right. Wait. So the surface Brillouin. So I have to use a surface termination to get any of this. I have to use a surface termination that's invariant under the MY mirror, right? So that's why I chose a surface, for example, that's with the normal in the x direction. But that was not quite your question, was it? Or maybe it was. Or the answer to your question, rather. No, this is not at the kx. That is the surface Brillouin zone. That's a system with a surface. So kx is not a good quantum number anymore. So there's only a two-dimensional. I mean, I wouldn't have needed to draw this in this 3D kind of way. I could have just drawn it plain. It's meant to be the Brillouin zone. So if you have a system in the slab geometry with x terminated in x direction, then only ky and kz are good quantum numbers. And this is the Brillouin zone of the system with the slab in the slab geometry. And these are the mirror invariant lines in that Brillouin zone. All right. Okay. Let me quickly, so it's actually quite nice. Let me mention one more example. It's also a bit of a more detached from an actual Hamiltonian. That so far you might have gotten the impression that these topological crystalline insulators are always forcing you to put some Dirac cone or something at a high symmetry point. But that is not necessarily the case. So I want to give you a second 3D example. And that is a system that is actually Fu and Fang in 15. And that's a system that is invariant under C2 times time reversal symmetry. Okay, so this is the symmetry that I ultimately want to look at. And I want to look at the surface that's invariant under a C2 rotation. Okay, so sorry, I changed my conventions, but before I get confused, I'll just use C2 set now. So I'll look at the set surface of some system. Okay, so this is the set direction, and I'll look at some system that's invariant under a C2 set rotation times time reversal symmetry. But before I do that, I would like to motivate this by starting with a topological insulator. So I want to start with a TI, a 3D TI, that is T invariant. And that's the only thing that I need to define a 3D TI. But it happens to be also C2 invariant for me. Just, I can make a C2 invariant TI. And then I can, then you know that there is the single Dirac cone on the surface. We heard about that yesterday. Probably is still very mysterious to those who haven't heard why that is there, but will remain mysterious. Okay, and so this surface Dirac cone, I can usually describe it, I can write this as a Dirac equation, and the typical choice is this one. So in Pauli matrices, sigma 1 times ky times sigma 2 times kx. Okay, that could be the theory for the surface Dirac cone. And it's there because I start with this 3D TI. And now I can ask what are the C2 set rotations. So, well, C2 set, first of all, is sending kx, ky to minus kx, minus ky. And to make that a symmetry of the system, the sort of matrix representation of this C2 set must be sigma 3, right? And time reversal symmetry, we know, takes k to minus k, and the matrix representation is I times sigma 2, that for the spin 1/2 fermions, right? So, and times complex conjugation, okay? So you can verify that this Hamiltonian is invariant under these two symmetries, but now I can do the following. I can take that product, C2 set, times T, and that will have the representation beside. So first of all, it will be local in the surface Brillouin zone, because if I only have kx and ky as good momenta, they are both getting inverted by C2 and by time reversal. So the combination of these two symmetries, it's a non-local symmetry in real space, right? But in k-space, it's a local symmetry. And if I compute it, I just get sigma 1 times k, okay? And so what that symmetry, now if I only care about this symmetry, it does two things. It disallows sigma 3 terms in the Hamiltonian, because this anticommutes with sigma 3. And I can shift, it's fine to shift the node of this Dirac Hamiltonian in momentum space. So I can write basically this Hamiltonian, I can write it as, so shift the Dirac node. I can write it as sigma 1 times ky minus, I don't know, some kappa y, but this is just a parameter, minus sigma 2 times kx minus some kappa x. Okay, and that's still invariant under this symmetry, right? And but I cannot get rid of this Dirac cone somehow, right? I cannot gap it out because I cannot put the sigma 3 term by this symmetry. So what it tells me is that on this set surface of a topological insulator, if I break time reversal, but in such a way that I retain the C2 times time reversal, the single Dirac cone is protected. It's not clear where it will be in the Brillouin zone. It can move around. But if I have only one, it's going to stay there. If I have two, I can actually annihilate them. So this is a C2 property. It's a C2 phase. But, well, it's there. So, so this is so C2 set times time reversal is a way to build topological crystalline insulators. And you see that this Dirac cone is only guaranteed to exist on the set surface. On the other surfaces, which are not invariant under C2, there's no need to have any surface states, right? They'll all be generically gapped under this perturbation, this imaginary perturbation, which breaks time reversal, but preserves C2 times time reversal. Okay, so that's another example of a class of topological crystalline insulators. And I think it's lunchtime. But questions? I mean, Questions or lunch? Yeah.
So if you don't think of like the 3D material as semi-infinite, but like so infinite in the same direction, and like think of it as a stack of.
So it's a finite slab. Mm-hmm.
You get like different, band dispersion, because then you won't break other mirror symmetries, I guess. That you break when you have the semi-infinite.
I'm not sure I understand. So you want to make, I mean, here, of course, I only look at one surface because they say the other one is so far away that there's no hybridization with the edge or boundary modes on the other surface. But that's the point, right? I just want to look at that surface sort of in an isolated way. I don't want to, yeah.
You don't think of it as the semi-infinite kind of thing?
No, this is, I can think of it as semi-infinite, but I don't quite see the difference between the two.
Because if it's semi-infinite, then if you have, let's say, mirror symmetry,
That maps one surface to the other. Yeah. Okay. So it's a question that I guess one could just gloss over and say, well, if it's mapping one surface to the other, there's no local constraint on one surface. So I can, whatever Hamiltonian I put on one surface, I'll make my mirror, I'll see two rotation, I put the same thing on the other surface. There's no constraint coming from such a symmetry. But after lunch, after Andre's next lecture, we'll have an example where actually such a mirror symmetry is important that relates to surfaces, and that will have to do with these higher order phases. So keep the question in mind. It's good.